Welcome back to ECE 441A, 541A. This is the pregame show. Oh, how many of you actually interrupted your tailgate to come to class? I don't know when they start, but anyway, the game is later today. But you now have a class, hopefully, that you will be able to get some information from. Homework number 6 is due in a week. That seems like it just appeared, but it's there now. Homework 7 is due the Wednesday following next Friday. And during that exam week, it's kind of a mess. We don't have class on Veterans Day. We don't have class on Wednesday, but look for material to be provided to you to get you ready for that exam, and I'll try to have office hours on the Tuesday between Veterans Day and that travel day. So keep your eyes and ears open. One more thing is today should be the last of our rules for root locus construction, and an additional lecture is in Unit 6 on the D2L website as far as which root locus pattern is it. You could have a pattern of poles and zeros, and depending on their relative location, the root locus is going to be different depending on how close or distant those poles and zeros are to one another, even though the pattern looks the same. And that 6E lecture, the 6 extra lecture, is on D2L, and that will probably be slid to the bottom of the stack relative to the material. I think lab number 3 is now available to you, but that will be essentially Unit 7 type material, and that's next week and the following week that we will be talking about how do we use these strategies, these techniques for design purposes. How do we figure out how to locate zeros, how to locate poles in our complex S-plane, and that's one of the reasons why we're learning these root locus drawing techniques or strategies, so that you get a feel for the impact or the influence of poles and zeros in the complex S-plane. Because now I'm guessing you're saying, well, why can't we just sketch it in MATLAB? You can, the diagram, but now how do you modify that diagram to make it move through more acceptable locations in the complex plane? That's the idea behind learning these rules. If you're in 541, there's deliverables that are due, and those dates haven't changed. Here is really just some information for you. It's giving you the answers, in a sense. If you're asked to sketch a root locus diagram, you can now build a transfer function in MATLAB and have MATLAB sketch the root locus. Hopefully you won't spend days trying to figure out why your MATLAB sketch or your root locus sketch doesn't match the MATLAB, because maybe you put the MATLAB system in wrong. So double check how you're entering the system into MATLAB, but that's why we're learning these as well. These strategies for sketching is now we have a way of self-checking or checking what MATLAB might be providing or doing for us. What we want to do today is actually look at finishing up the construction rules, which is rule number 6, and then if we have time, we'll go ahead and start just working through some examples. And before we do that, let's just scroll through these construction rules. And if you're looking at exam 3 material, which is now available, you'll see that some of the problems on that exam, there's more problems than 5 or 4. There may be 9 problems on exam 3, but they're pieces. For example, I might ask you to create or plot the poles and zeros and shade the region on the real axis that belongs to the root locus. That might be a question. But I'm really just trying to break up these rules into little pieces so that I can assess your understanding of those pieces. Rules 1 and 2 might actually be a problem on the exam. Where can you count poles and zeros, and do you remember even and odd? That's basically rule 1 and 2. Asymptotic behavior. Where are those asymptote angles? At what angle? And where are they centered? And I might ask you something that sort of mixes 5 and 3. I might even ask you, where does the asymptote line cross the imaginary axis? And that essentially is rule number 3 with a little trigonometry. It's not the exact location of the root locus branch that's crossing the imaginary axis. It's where does the asymptote cross. But we also should realize that the branch of the root locus is going to be probably somewhat close to the asymptote depending on where the centroid is located and where it's broken away from the real line. And the breakaway and reentry points, I might ask you to circle on the exam. Where do you expect, and now I don't remember, I tell you to circle one and box another, but box maybe the region where you re-enter and circle where they break away. Meaning you might have breakaway and re-entry points on the real line, and I hope that you have a intuitive feel for where those might be occurring and how you might determine when that's happening. And the last two rules really hinge on the phase angle condition. The sum of the algebraic sum of the poles and zeros of G of S and H of S need to sum to minus 180 degrees, and that gives you another way of determining. If I just give you a point in the complex S-plane and say, is that point on the root locus, or is it close to the root locus, adjusting for calculation errors, meaning close, but are we close to minus 180 in that region around maybe the given point? Here's rule number 6. This is one maybe we haven't yet talked about directly, but we've made our way close to it, and that's concerning angles of arrival and angles of departure. That's the label. I would label it angles of arrival and departure. Where do your branches, or in what direction or at what angle do your branches of the root locus depart from complex pole pairs? And what's the angle when they are arriving at complex zeros? And really, here's the strategy. I don't have my student here that I was going to emphasize on this epsilon, but he'll show up maybe in a few minutes. We'll see. But we pick a point close to the pole or zero, an epsilon distance away, so that essentially when we're calculating the angles from the other poles and zeros, we're right at that pole or zero that we're asking whether or not, or what is the angle of departure or arrival. So we pick a point, S sub theta, very close to that location in question, and then we just apply the phase angle condition. This may not make any sense right now, but here's a picture. Here's two different scenarios. The one on the left is concerned with complex conjugate poles, and we're really wanting to know right at that pole, you draw a line tangent to the branch, and now you can form an angle theta sub d. That's what I'm calling the departure angle. We want to figure out what is that angle. That's rule number 6. We can also apply that to the angle of arrival. How is the branch approaching that finite zero? It's a complex zero, so it's coming in at a particular angle. We want to calculate theta sub a. Obviously, when you're calculating these, you won't have that red line there to begin with. That's what you're trying to sketch. So you're trying to figure out, how do I draw these green sketching lines or angles so that I can shape my branch, my root locus branch, as it approaches or departs from the zero or pole respectively. Is that clear? So we're trying to calculate theta sub d or theta sub a. We're only calculating one of those for the complex pair. It's a mirror image, so once we have theta sub d upstairs, we can just mirror that downstairs and we know how the branch departs from the pole below the one in question. Let's look at an example. I'm not sure I'm going to get all of this on, but here I have factored the numerator polynomial in our way to hopefully identify mentally where those zeros are located. We have an s plus a quantity squared plus a b squared, and that gives us then a zero, complex zero pair at -2 plus and minus j2. And that's where the other zero will be that's right now cut off from that, but I'm for some reason nervous about trying to collapse that to fit it on one page. I don't know why. I might as well take a little bit of a risk. So there we go. So we're living dangerously now, but that's the picture. We have two complex conjugate zeros, and we have three poles, and I've exaggerated those poles at the origin so that you can see that I have two x's. But those x's are theoretically right at the origin. Is that clear? So don't think, well, he can't even locate poles at the origin. Well, maybe I can't, but I'm trying to indicate or emphasize that I do have two of those x's at the origin. And now you can see how many angles are involved in this phase angle condition determination. We have an angle for each of the poles at the origin towards that zero in question. We are trying to find what is theta sub z sub 1. What's the angle of the root locus very close to that zero at -2 plus j2? And to calculate that, we need to figure out all the other angle contributions from the remaining singularities. And we can compute those because we know exactly where that zero is. And I've created this problem to make our calculations not even need a calculator in this particular case. We can see by inspection or by just knowing that we're dealing with a lot of 45 degrees and 90-degree angles. That's the picture. So the very first thing we do is we plot down our x's and o's, and then we say, oh goodness, where is that branch going to come in at? It's where are the branches beginning? What branches do we have in this diagram? I didn't even indicate real line segments for the root locus, but can you see those virtually? Put on your virtual headset. Did you know this was a virtual reality class? Man, now you can put that in your conversation when you're interviewing. Yes, we talk virtual reality in my controls class. But we try to imagine now what's going on with respect to how many pieces. So maybe you shouldn't go this far and start talking about bread in your interview, but if we had bread on that real line, how many pieces would we have? Those two poles at the origin just cut the loaf once, don't they? They cut it at the origin. We have a segment of the bread from 0 all the way to plus infinity. We have a segment from 0 to -4 and a segment from -4 to minus infinity. Which of those segments are on the root locus? There's only one, isn't there? There's three pieces, but we only have one, and it's from -4 to minus infinity. What's our pole zero excess? What is our pole zero excess? It's just one. So we just have one asymptote, and that's going off at minus infinity. Everything else has to be in the finite S-plane. And that's why we're expecting then these two branches to arrive at those two complex zeros. And they are going to depart. They immediately, as soon as we start cranking up the gain k, we immediately depart from the poles at the origin. And those branches are now going to go up and towards those zeros. And we are now in the first part asking, how are we approaching those zeros? And here's an exploded view. Here's the epsilon that I was talking about. And I've tried to identify this point that's an epsilon distance away. At a very tiny distance, but once you move off of that zero, you now are going to have an angle associated with that location. We don't know where that dot is. We're trying to locate it. But now it's within some epsilon, and if we figure out the angle, we know exactly where that dot is. So if we can calculate theta sub z sub 1, or the arrival angle, theta sub a, then we will be able to draw or finish our root locus sketch. Questions on what we're trying to do? I told you I was living dangerously. Sorry for the delay, but now we're back at 65%. Not for your exam, but for the lecture screen size. Okay? All right, here we are. Let's do the phase angle condition for this particular problem. And what does that look like? What's the phase angle condition associated with this system? Or what is the phase angle condition just in general? If I had to now write it down, do I have some summation symbols? Maybe. And what do I have first? I have angles that I'm summing. Which ones? Poles or zeros? Now I have g of s, h of s as a ratio of polynomials in S, or a ratio of factors. And now I just say, oh, I have my zero factors, which are upstairs. Those get added in, and I subtract the zero factor angles that are downstairs. I'm now saying I have the angles of zeros of g of s, h of s, minus the sum of the angles of the poles. And I know that for that point, s sub theta, to be on the root locus, this sum of angles, algebraic sum of angles, needs to sum to minus 180 degrees. So I can immediately just set that entire left-hand side equal to minus 180 and solve for the unknown angle, which is the theta sub z sub 1. This is to allow us to say that for the point s sub theta to be on the root locus. That's why we can set it equal to 180 degrees. So now let's use that angle condition to find the angle of arrival at the upper complex zero. You could calculate it for the lower one, but just traditionally or generally I just work with the top one, the upper. But you have to pick one and then stick with it. In this case, now we have theta z1. That's the angle associated with the complex 0 at z1 plus the angle of z sub 2's angle minus theta p1, theta p2. Those are the angles due to the poles at the origin plus theta p sub 3, and those now all need to sum to minus 180. Here's the angle that I really am trying to find. So this one is the unknown theta sub a. If that's the case, then I can leave it as an unknown. But what is theta sub z sub 2? Now I'm asking, what's the angle that I have to look to or move to get from theta sub z sub 2 up to theta sub z, or up to the z sub 1? What is that angle? It's straight up, so that's 90 degrees. Theta z sub 2 is 90 degrees. What's theta p sub 1? What's the angle from the origin to that 0? And now if I measure the acute angle, I'm up 2 and over 2. That's 45. And so theta p sub 1 is 180 minus 45. And I have two of those. I have two poles at the origin. Both of those have the same angle of 135 degrees. And what's theta p sub 3? That is an acute angle, up 2 over 2. That is 45 degrees. I told you I cooked this up so that we didn't have to do too much thinking. But now we have this theta sub p sub 3 is 45 degrees, and all of those are now equal to minus 180. And now we can do some simplifying. Here's 270, and then that combined with plus 90 gives me minus 180, and that minus 180 can cancel on that side, and I'm now really left with theta sub a minus 45 degrees is equal to 0. Or I now know what my angle of arrival is. Theta sub a, the angle of arrival, is 45 degrees. And that's the angle that I now want to come into that 0, that upper 0, as I sketch my root locus branches. And in fact, I've sort of drawn that maybe a little bit bigger than 45 degrees in this sketch. But now you can know exactly how you're going to come in or approach that 0 at minus 2 plus j2. Now, how do we depart from the two poles at the origin? We could consider those to be complex conjugates. They're at 0 plus and minus j0. Let's just use this same idea to find the angle of departure. From the poles at the origin. Or in particular, here's the sketch that I have. I have these two poles. I have a 0 here and its mirror image there, and then I have a pole there. This is minus 4. Here's minus 2, j2, and minus j2. And I'm really wanting to know, there's an angle. I could call that theta sub z sub 1. I'm looking at the point close to the origin. And here's my theta sub z sub 2. And there's theta sub p sub 3. I don't have to move at all. I just have to look straight ahead or at an angle of 0 for theta sub p sub 3. But now if I was a small distance away from here, assume that's epsilon close, this could be my theta p1 or my theta p2. Is that clear? And I'm trying to find where is that dot in terms of angle from the origin. And I can simply do my phase angle condition. I haven't changed the number of poles or zeros, but I have changed these angles because I'm now looking at a different location in the complex S-plane. What's theta sub z sub 1 in this part of my root locus sketching process? I'm down 2 and over 2, so that's minus 45 degrees. What's theta sub z sub 2? That's 45 degrees. Those two are actually going to cancel, but I now have minus 45 degrees plus 45 degrees minus, and the theta p's, these are the unknowns. These are the ones that I'm trying to solve for. And they're actually going to be the same, so I'm just going to call those theta departure, and I'm going to have 2 of those. I have 2 angles contributed by each, or I have 1 angle contributed by each of those 2 poles at the origin. And what's theta sub p sub 3? We said that was 0 degrees, and all of that is minus 180. And now I have minus, or if I multiply by minus 1, I end up with 2 theta sub d is equal to 180 degrees, or the departure angle now is 90 degrees. So I'm going straight up from one of those poles. I'm going straight down, and now I can say, oh, there's where that goes, and I come in at 45 degrees. So if I'd drawn this accurately, which I haven't, what in the world am I doing? I said I'm symmetric, and I wasn't symmetric, was I? So I need to be mirror image of that, and now this does something like that, and that does something like that. And this one goes off to minus infinity. And that's my sketch of that system's root locus diagram. Are there questions on that? You now know how to use rule number 6. It's really just applying the phase angle condition. So now let's look at another example that's not rule 6. It's just a generic root locus example. And suppose that we're given for this, g of s is k, s plus 4 over s minus 2, s plus 3. Again, don't lose track of what we actually have. We actually have that g in a closed loop configuration with negative output feedback. Here's r of s, here's y of s, and we want to know what's the pattern of possible closed loop pole values for this particular g of s as I adjust k from 0 to infinity. And what's my first step in sketching this root locus? If I didn't have that feedback path, how would this system behave if I hit it with a r, with a reference input? If I just had g and maybe a gain k, but I didn't have any feedback, this is open loop, if that feedback path were disconnected, what would happen? Would everything be okay? Can you tell me, based on G, where are your poles? You have one that's at +2. That's going to go to e to the 2t as far as its mode. You hit this or excite this just a little bit, you're unstable in an open loop setting. So you have to stabilize this, or you have to now apply some kind of feedback in order to change the dynamics if you want a stable system. So in this case, to sketch the root locus, now I've forgotten what I started with. Oh, I had a pole at 2 and a pole at 3 and a 0 at -4. That shouldn't be that difficult, right, to put that down. Now, which segments of the real axis belong to the root locus? Is the line segment from +2 to infinity on the root locus? No. What about the segment between -3 and +2? If I'm anywhere between these two, I have one pole, an odd pole to my right. So that piece of the real axis, it belongs to the root locus. The segment between -3 and -4, is that on the root locus? No. What about from -4 to -infinity? Yes. So now I have my segments that belong to the root locus. What's my pole 0 excess? It's 1. So how many branches of my root locus going off to infinity do I have? I just have 1. That's equal to the pole 0. So I have 1 branch of my root locus going off to infinity. And what's the angle that it's approaching infinity? 180 divided by that 1, or it's going off at 180. So I eventually will have a branch going to the left and 1 branch approaching that finite 0. And initially, when I start adjusting K, those two branches are going to start going towards each other from +2 and -3. Now what happens? What can we do now? We've already talked about the branches, the asymptotes. We're up to rule number 4 if we were just doing this a brute force. But if you remember our story of 2 poles to the right of 1 0, 2 poles walk into a bar and they're to the right of a 0. Kind of is what it, but maybe now you'll remember. 2 poles to the right of a 0. What's that give us? You're missing out if you're at home, but we're doing all sorts of hand signals. It's game day, so we might as well do something a little bit supportive of our team. But we had a wildcat, but we really were focusing on the 0, right? Or actually a circle. So now we have a circle that is going to connect the breakaway from the reentry. If you now had to, on an exam, circle the breakaway and box the reentry, do you understand where you would maybe draw a circle or an oval and where you might draw a box? In this particular case, with 2 poles to the right of 1 0, you actually can find the breakaway knowing that structure by calculating the geometric mean from that 0 to each of those poles. By that I mean the following. What's the distance from -4 to -3? So now I'm actually asking, or, I don't want to do this in red. We'll do it in black. Here's the radius that I'm interested in. I'm just going to call it R. And it's the geometric mean from the 0 to those two poles. And the first one, so the geometric mean is not a plus b over 2. It's essentially a times b square root, or a times b raised to the 1/2. So the geometric mean now is going to be, let me just say that it's 4 minus 3 for that distance to try to emphasize what I'm doing. And then it's the distance between the 0 and that pole way over at 2, which is 6 away. So in this case, I'm really looking for my radius being the square root of 6. What do I mean by the radius? Did everybody bring their compasses? Now the center of that compass is right at the 0 at -4, and the pencil end is a radial distance away, and now we can simply draw that distance in. What is the square root of 6? Did I ever calculate that anywhere here in my notes? Let's just say it's about 2.45. Now we walk 2.45 units to the right of -4, and we could actually go to the left of -4, and that now identifies our breakaway and reentry points in the complex S-plane. So what would be 2.4? We go over here and we're at about, what, 1.55? And then we start circling. And then we go over to minus 6.45, and we're right there. And I know this isn't going to be a very good circle, but that's what it's supposed to look like. Where now we are approaching, and now these. Here is our breakaway. At S equal the difference between -4 and adding 2.45. Isn't that now minus 1.55? And this reentry, this is our radius away. That's R. This reentry is now occurring at S equal to -4 minus 2.45. And that's now our root locus diagram. What if we forgot that story? 2 poles to the right of 1, 0. And you forgot that that's how to sketch this. How would you apply now rule number 4? Rule number 4 would say, oh, what's the breakaway or reentry? And how do you find the breakaway point from rule number 4? What's that based on? And now I've given you a big hint. It's the magnitude condition. It's now K, S plus 4 over S minus 2, S plus 3 equaling 1. Or if we solve that for K, we have something like that. And now you could plug in different values of S. I hope you can anticipate a breakaway between S equal plus 2 and S equal minus 3. So you're evaluating that K expression between those two extremes, and you're looking for a relative maximum. If you wanted to, you could maybe, if I've done this right, you could do that on your calculator. you could plug in this ABS of what we just said. We have x minus 2, x plus 3 divided by x plus 4. And now we just sketch that, and we could do the maximum function on our calculator, and it's going to find that that occurs at minus 1.55, and the value of that maximum is 2.1. What's 2.1? What's that correspond to? In fact, what we're doing is if we evaluate this at 1.55, that's going to be 2.1. So on this dial of k, we go from 0. When we're at 0, we're at plus 2 and minus 3. We crank up the gain k, and we dial that knob up to 2.1. Then that pole that started at plus 2 is now all the way over to minus 1.55, and that pole at minus 3 has gone into minus 1.55. So it's definitely not halfway between those 2 points. Do you see that? And that's because we have another 0 or another singularity in our plant or in our system. What if now we go back and I say, can you find, so now if I crank up the gain to 2.1, is my system stable? If I now have this in a closed loop configuration and I crank up the gain k, your boss says, stabilize this unstable system. And you go, okay, I'll do it with just a gain controller, just with a gain, and I'm going to crank up that gain to 2.1. Is your closed loop system going to be stable if k is 2.1? What can you tell your boss if k is 2.1? Can you tell him anything other than, I don't know, I think it's, I don't know, let me call someone, or I'll get back to, no, you don't need to call anybody, you don't need to get back to anyone. What do you know? If k is 2.1, where are my closed loop poles? How many closed loop poles do I have? Can you answer that? How many closed loop poles do you have? How many open loop poles did you start with? 2. Did you put any additional poles in there with your controller? Your controller was just a gain, so you haven't changed the system order. You now have 2 closed loop poles. And with k equal to 2.1, where are those closed loop poles? Really? Oh, I was on the other page. No wonder. Maybe you forgot the page number. If I'm at 2.1 for k, where am I? So here's maybe what's confusing. That blue line, is that the root locus diagram? No, that's just the value of k. That's this function k for these different values of s. So don't get confused. This is not a root locus diagram. Is that clear? So this is just showing me how k varies as I evaluate that expression for my gain at different values of s. Between, well, here it's showing from about 10 up to minus 5 or something. But it's going crazy from those places, isn't it? And does it really matter what it's doing to the right of plus 2? No, we're not concerned with that. That's not on our root locus. All right, so where are my poles at k equal to 2.1? Aren't they right on top of each other? Aren't they two real equal poles at minus 1.55? Is your system stable? Yes. Now, what's the minimum value of gain K? So we could start asking all sorts of questions. What's the minimum value of gain K to make that system stable? Now you've verified to your boss that K of 2.1? So 2.1 puts you at minus 1.55 and minus 1.55. What's the gain necessary to stabilize this system? Can you figure out how to calculate K to stabilize the system? Do you understand what this root locus diagram is providing? It's telling you how the poles, the closed loop poles, migrate as you crank up the gain K from 0 to infinity. If K is 0, where are your poles? Plus 2 and minus 3. They're unstable. You crank up the gain K, and what's happening to that pole at plus 2? Is it moving in a better direction? Yeah, it's starting to go to the left half plane. That's where you want it to go. And you can see that if you crank it up to 2.1, they've both moved, but they now are both inside the complex S-plane. What if it was at 2 for K? What would you expect? If you just back off a little bit, would you have complex poles, closed loop poles, if your gain K was 2? Do you have real equal poles if your gain is 2? No, you have real unequal poles. What if the gain was 2.5? Now where are your closed loop poles? Now they are complex conjugates. They've broken away. What's the gain to get us to be stable? Could you now calculate the gain? That's now a cloud, and that's a cloud. I'm speculating where that second cloud is, but the first cloud, you could calculate the gain with S equal to 0 in our gain expression and find what's the minimum value of K to stabilize this system. To stabilize the system now, for stability, we could say, oh, K is now S minus 2, S plus 3 over S plus 4, evaluated at the cloud. But that cloud is what? In this case, that's the origin. And that's not too hard to calculate, is it? You can do that even without a calculator, if you wanted to. So now you have 2 times 3, 6, divided by 4. So what's the minimum gain to get you a stable system? You need to crank up that gain at least to 1.5 to get it stable. Is this making sense? What if you wanted to locate your poles at, I don't know why I picked these, but let's just say that now you want poles at minus 2.27. And now you know how far that triangle is away from minus 4. You know that distance, right? This is now this is the square root of 6. And I actually picked that triangle to be, or I now am wanting each of those parts, the vertical part and the horizontal part, to be equal. So I wanted this to be a 45-degree angle from that 0. So that distance going up is square root of 3. The distance coming back is the square root of 3. That's where I ended up with this being s equal to minus 2.27 plus, well, it's not minus, but plus j 1.73. It's the square root of 3 up off of the real line. Now you can just plug that in to get to, what did I say that was, a triangle? So now k triangle is going to be the same exact expression, but now it's going to be at the triangle location, which is now minus 2.27 plus j 1.73. And you could plug that complex number in for s, evaluate those magnitudes, multiply them out. Did I even do that? I don't even know if I did it. But you could now ask, is that point on the root locus? How would you solve that? Is that triangle really on the root locus? How would you answer that question? That point of minus 2.27 plus j 1.73. Is it on the root locus? How would you find? You could use the phase angle condition and evaluate the phase at that value, that complex value of s, and what would you want that phase of g to be? Minus 180. So if it's a negative number, you've got it. We'll pick up with design questions next time. How do we design controllers to shape or move these poles, closed loop poles around in our complex S-plane?